Hello, this video is for CIS200 Unit 5 challenge work. So this is on page 17 of lesson 2. We would go ahead and click launch activity. I already have it open here in Cengage. So it is easy to write a sequential algorithm that sums up a 100 element vector. It would look something like this. Assume that instead of having only a single processor, you have 100, etc. Read the rest of the question and then dive into answering it. So we'll go ahead and call this Q1. So we'll say something like with a binary tree structure, we can add pairs of numbers simultaneously instead of one processor adding numbers one by one. So it'd be like a parallel algorithm, right? So we could say like for step one, we'll say 50 processors, add pairs of the 100 numbers. This would give 50 sums. Step two, 25 processors, add pairs of those 50 sums. Resulting in 25 sums. Step three, 12 processors, add pairs with one sum left on standby, resulting in 13 sums. Step four, or steps 4 through 7, right? Because we got to continue pairing them up. So we'll word it that way. Continue pairing up and adding the remaining sums until only one final total is left. Now let's address the speed and processor section. So we'll just call it speed and processor. So it says something like how much faster. So to answer that, we know that the sequential algorithm takes 100 time units, whatever the unit is for time. Our parallel tree method takes only 7 time units because log base 2 of 100 is equals approximately 6.64. So we'd round up to get the 7 time units. This is roughly 14 times faster. Now, do we need all 100 processors? No. As seen in the first step, we only paired up 100 numbers, which requires a max of 50 processors, while the other 50 set idle. Using more than 100, scroll up some, more than 100 processors would not help because we cannot add fewer than two numbers together. So the extra processors would just sit there, not being utilized. Alrighty. So now this answers question one. We would continue with the same thing, save the document, and then save it again as a PDF and submit it. We'd submit it right here, and we go to the next one. The next one talks about the von Neumann architecture, and then von Neumann processors, such as the Intel Quad Core and the A10 from Apple. And it has a few items to examine, right? And it wants a report describing real world characteristics of a processor you selected. So I'm just going to discuss the Intel Core i7 for question two. Go ahead and call this Q2. State the processor that we selected. And then begin our little report. This processor follows the von Neumann model, but is much more advanced than the simple machine presented in the questions figures. Well, let's talk about some characteristics. As far as the i7's instruction set, you would just look them up, right, for whatever processor that you chose. So the i7 uses the x86 TAC 64 instruction set architecture, which is abbreviated as ISA. It contains thousands of complex instructions. Now let's talk about register availability. An i7 contains dozens of 64-bit general purpose registers, which is a lot more and more capable than the registers presented in the questions figures. And these are the figures that I'm referring to here and here. We can talk about cache memory. The i7 uses L1, L2, and L3, a three-level cache system, which is built directly into the CPU chip. Let's see, speed. The i7 operates at speeds ranging from hundreds of G flops, which is billions of floating point operations per second, to multiple T flops, which is trillions of operations per second. So G flops, billions, floating point operations, T flops, trillions floating point operations. We can talk about memory and addressing. The i7 can address up to 64 gigabytes or more of physical RAM, much more than that in the figures. And then we can talk about memory chunks and access time lastly. An i7 reads memory in large 64 byte chunks, right? Which are referred to as cache lines, resulting in ultra fast access times measured in fractions of nanoseconds. And approximately 50 to 100 nanoseconds for RAM. And this fractions of nanoseconds is for cache. So resulting in ultra fast access times measured in fractions of nanoseconds for cache and approximately 50 to 100 nanoseconds for RAM. Go ahead and save and submit, save the document so that you have it just in case, then save it as a PDF and submit it right here within Cengage. And that is the final question for CIS 200 Unit 5 challenge work. Thank you. Have a great rest of your day.